structures and thermal axial deformation, and 1 in torsion. Okay. Screen is disconnected, so I'm just gonna wait for it. Okay. So we're gonna start from the statics section. The first question that I'm gonna solve is this one. It's from chapter 4. I'm gonna give you guys 1 or 2 minutes to think about it, and it would really help you guys a lot if you could actually try to solve it, at least in your head. So do you have any ideas on how to start solving it? Free body diagram, yeah. So the first step of every statics and mechanics of material question is drawing the free body diagram, and if you draw it correctly, you'll most likely get an idea on how to actually start and solve the problem. So I have already drawn the free body diagram here. So for drawing the free body diagram, you remove all the supports and you replace them with forces or moments, if applicable, okay? So here you see we're in a 3-dimensional space, and all of these joints can have X, Y, or Z components. So I have replaced both supports with X, Y, and Z components, and I have replaced the cable with a set of force, TBG and TBH. Okay? Does the free body diagram make sense to you guys? Do you have any questions on it? No? Okay, so now, yeah, go ahead. Oh, the blue line, yeah. I was gonna get to that. So, let me just delete the blue line first. Okay. So, what is the next step after having the free body diagram? Yeah. So you have sigma f of x equal to 0, sigma f of y equal to 0, and sigma m around any point, let's say, equal to 0. So which one would you start first? What is known here? The P. Let me just draw the P in a different color. So we know P and we know nothing else. right? P is known and nothing else is known. Where should I start? What? In the Y direction? Why is that? Yeah, but I have so many unknowns in the Y direction as well, right? I don't know. So basically, if you want to start with sigma f of Y, you don't know AY, you don't know DY, and you don't know the Y components of TBG and TBH. Okay? So in such conditions that you have too many unknowns, the only way to approach your question is by starting from a moment. Why? Because a moment, if you choose the point or the axis that you want to take the moment around it, if you choose it correctly, you can get rid of all of your unknowns, or at least some of your unknowns. Okay?
Did you use the mic?
The mic? Where is it? How do you open? You mean I'm not loud enough for them to hear? I've never done this before.
Let's see if
there's battery in it. Ask. What? Finding moments at A? Is there any place I can hang this on? Oh. One, two, three? No. Upside down. 1, 2, 3. Is it better? Can you guys hear me? Closer up. Can you guys hear me now? Is it better? Okay. So, I was saying that when you have too many unknowns, like in this one, the best approach is to start from taking the moment. And where can I take the moment so that I would get rid of some of the unknowns? What? Line? AD, yeah, correct. So, as you know, if the axis that you're getting the moment around, you're calculating the moment around, passes through the forces, so those forces do not cause any moment around that axis, right? So if I create an arbitrary axis from point A to point D, okay? And I can do that because they're both point A and point D are kind of our ground here, are kind of the support here, right? So if I connect these two and come up with an axis AD and take the moment around AD, then I won't be needing to worry about all the components of dx, dy, dz, or ax, ay, az. So I have 6 unknowns that I don't need to worry about if I take the moment around AD. Okay? So I would write sigma m around AD is equal to 0. And then I have to come up with the vectors for AD and the connecting vectors relative from point B to the axis AD. Okay? So AD itself is I hat minus 0.75 k hat. And you're familiar with I and j, right? The unit vectors. Okay, hopefully you're familiar with them. So connecting from here to here, I have two 0.5, which will result in 1 in the x direction. So that's where I got I. And negative 0.75 from point A to D in the z direction. Okay?
It's stuck at the first line.
The Google Meet is stuck at the first slide. So I share entire screen.
If you go back,
Is it good now? And if I go to the next one, does it go to the next one? Yeah? Okay. Okay. So where were we? Okay. We have written down the vector for AD. Similarly, we have to write down the vector for BG. So for BG, it will be negative 0.5 in the I direction, plus 0.925 in the J direction, and negative 0.4 in the Z direction. Okay? Just raise your hand if you have any questions regarding this, okay? So similarly, we can write the vector for BH, and it's 0.375 in the I direction, plus 0.75 in the J direction, negative 0.75 in the K direction. I need the relative vector from point B to point A. So I'm gonna have to write down the relative vector from B to A, which is 0.5 in the I direction, and the relative vector from C to A, which is the unit vector I. Okay? Next, I need to find the tension vectors for these two components, TGH, TBH, and TBG. Since it's a cable, the tension magnitude in the cable is equal. So we have 1T here. So the tension magnitude is equal, but because they have two different orientations, the vector will be different for each of them. Okay? Does it make sense? So the vector for BG will be its magnitude T times BG vector over the magnitude of the BG vector. Does it make sense? Okay, good. And are you guys familiar with how to calculate this? So I'm just gonna skip the part and give you the final answer. It will be T times negative 0.444 I hat plus 0.822 J hat minus 0.355 K hat. Similar to this, if we write T of BH, it will be T times BH divided by the magnitude of BH, which will be T times 333I plus 0.667 J minus 0.667 K. Okay? Now, lastly, what we need to calculate is the vector for AD. So lambda of AD so I'm just gonna write down this one for you guys. So if you're not familiar with it, there is one example for it. So will be the vector of AD divided by the magnitude of AD. Okay, so the vector of AD we calculated, it's here, I minus 0.75 K. So I minus 0.75 K divided by 1 to power of 2 plus 0.75 to the power of 2, okay? Which will result in 0.64 I minus 0.48 K. Okay. Having all of them, now we can proceed with this equation. So, can anyone help me to write down this one? So I want to write the moment around line AD. I know that none of the components of support A and support D have any moments around AD. So the only forces that actually act around AD are these three: TBG, TBH, and P. Right? So, which one should we start with? Let's just start with TBG. So, you have from point B to point A, you have the relative vector RB relative to A cross the force vector of BG. Okay? This will give you the moment around point A, and then a dot product with the unit vector of line AD will give you the moment around line AD. Does it make sense? Lambda is the unit vector for line AD. Yeah. So for line AD, the vector is I minus 0.75 K. And we calculated the unit vector of it here. So lambda is that. Okay? Go ahead. And can't hear you. What's the difference between lambda and what? You're asking why I multiplied this one with T, but not lambda? Yeah? So this one was a force. So TBG represents the force inside the cable, okay? So there is a force there. But AD is just a vector that I created. It's just a line, and there is no force in AD, right? So there is no need to multiply lambda with a force, right? Does it make sense? Okay. Okay, so this part represents the moment caused by TBG, right? So similarly, you guys help me out how to write the second part. So for BH. Anyone wants to give it a shot? Mm-hmm. Exactly. So the relative vector from B to A times TBG will give us the moment caused around point A by the force vector BG, and then a dot product with lambda AD will give us the moment around line AD. Okay. And lastly, we need to calculate the moment caused by P. So it's going to follow the same trend. The only difference is yeah. Oh yeah, so my bad. The other one is BH. Thanks. So for force P, it will be lambda AD dot the relative vector from point C, which is here, to A, times the force vector P. Okay? Yes. It's the same. So the only thing that we haven't actually written down is the vector for force P, which is really simple, right? Let me write it somewhere. Okay, let me write it down here. So force P has a magnitude of how much? 268 newtons. And it's in the negative y direction. So it will be negative j hat, right? And this is equal to 0. Okay? So basically, the statics part of it is done. The rest is just mathematics and solving the equation, right? So when you reach this point, you can take a deep breath and do the math, okay? Any questions up until here? Are you guys familiar with the matrix multiplication, or do I need to go over it? Is there anyone who doesn't know the matrix multiplication? Good. So writing the matrices and calculating the determinant, you will end up with an equation from which you can find T to be 360 pounds. Go ahead. No, because it's a rope. A rope or a cable, when you have a cable that goes through a point, like here. No. So the tension inside the cable is the same, okay? But TGH and TBG and BH are different because they're in two different directions, okay? Go ahead. So the only unknown here, because we took the moment around line AD, so the only unknown here is inside TBH and TBG, okay? And TBH and TBG are T times a vector, right? So the only unknown in that equation is T. Does it make sense? Go ahead. I can't hear you. No more questions? Okay. Let's move on to the next question. The next question is a truss. The tricky part about this one is that the force is being exerted somewhere in the space. So this is to represent if let's say we have a weird distribution here, some concentrated force here, I don't know, a moment here, and finally we calculate everything and replace all of them with a single force acting at an arbitrary point. Okay, so given we have that, we want to calculate a bunch of things. So I will let you guys read the question for 1 or 2 minutes. Try to come up with possible roadmaps for solving the question, and then we're gonna see how it turns out. Guys, you don't need to take pictures because we will upload the PowerPoint, the PDF, okay? Okay, now anyone with a suggestion on how to start? Go ahead. I can't hear you. Uh-huh. From which link? From which section? So the whole top part, something like here. Okay. What does that give you? If I isolate this, I have force acting here. Okay. And I have, let's see, these structures, right? So if I isolate this part, what does it give me? I can't. Can we turn off the fan? These two? Okay. Hmm. Okay. So there's so many things that we don't know here, like the force acting on C, the force on F, uh, and the forces in these links, uh, BC and BF, right? So I need to choose a section or a way to isolate most of them and be left with only a couple of forces so I can solve using the equilibrium equations, right? Go ahead.
Down part where we want to solve.
This part? Okay. So, yeah, that will actually not work because you gotta solve for C first. Yeah, because you have a force here and you need to solve for it. So the best way to approach this is by isolating this part and having these forces. Okay? So by doing so, you will end up having something like this, and you want to solve for Cx, Fx, and Fy. Bar BC because I'm solving in basically in this frame separately. Okay, so there are two frames connected to each other. We can write the equations for each frame separately, right? So each frame needs to be in equilibrium by its own. Okay? So what I will do, yeah. The tension that what causes? Mm-hmm. Yeah, but I didn't understand your question.
Usually when you do a cut, like you have something that's like attached to the
Mm-hmm. It's something attached to it, like this part. Uh-huh.
like you get tension force or
So, depending on which side you want to keep, you can get rid of the other side, right? I decided to keep the left side, so I decided to keep the left side of CF. So now I only care about the forces at F and C. If I wanted to keep the other side, for example, if I had a support somewhere here, and for some reason I wanted to keep the other side, then my forces would have become basically my forces would have become something like this: Cx, and then something here and something here. Let's say F and Fk. Because I'm keeping this side of the truss. Think about it as if the acting force from this component is represented through both Fx and Fy. Okay? So some portion of it goes to Fx, some portion of it goes to Fy. Somebody else had a question. Oh, it's because it's given in the question. It says at point C, it can only transit a horizontal force. Okay? Any other questions? Okay, so what should I do now? Somebody who, someone except you and you. Someone else, please come up with a suggestion. What? Moment at F. Why? So, in other words, guys, if I want to start from sigma f of x, I have two unknowns, cx and cy. So I have one equation and two unknowns, and that's useless for me. If I want to start at sigma f of y, I can do that. I will have fy, but again, I don't have cx and fx. Okay? So the only equation that will give me cx is a moment equation. And I need to choose carefully at around which point I will calculate the moment. So you always calculate the moment around the point that has two unknown components, obviously, because in that way you're only left with one unknown and you can solve it through the equation, right? If no such point can be found, then you're just gonna have to solve a system of equations, right? Like 2 equation, 2 unknown, or 3 equation, 3 unknowns, okay? So for this one, if we take the moment around point F, the effect of Fx and Fy will be cancelled out, right? And we're gonna have 1200 times 30 minus cx times 18 equal to 0, right? And from here, you can calculate cx to be 2,000 pounds. What next? The rest is easy, right? You do sigma f of x equals 0, and the only unknown for you is f of x, which is equal to cx, and equal to 2,000 pounds. And then you'll do sigma f of y, and you'll get f of y equal to 1,200. Yeah, negative. So I assumed upwards positive. So this one is positive. And so this is not a vector, it's just a value for fx. Fx is acting in the opposite direction of x. So if you want to show it in a vector representation, it's negative, but this is just a value. And I've chosen the direction correctly. So, okay. The next part, we want to solve the force in BE. In order to solve BE, I will just take the elements A, B, C and write down the free body diagram. So this was free body diagram of frame. This is the free body diagram of a member. Okay, what can I write for this free body diagram? Moment around A, why? Yeah, exactly. So I know Cx, I can solve for FBE if I take the moment around A. Okay, so I've solved part A, the force in link BE, we have it now. And then part B, it is asking us to find the components of the force exerted by the hydraulic cylinder on pin edge. So here it is asking us to find this force. So if I want to find the forces at BH, at point H, which elements should I isolate and draw the free body diagram of? Anyone? So if I take this member and this member and isolate them and draw the free body diagram for them. So it will be the the free body diagram of DEF and HE. Okay? So at one end, I have the unknowns of F. At the middle, I have F of BE, which I have already calculated. And I have the support at D. And then I have the cylinder force, HE. Okay? For simplicity, I'm just gonna leave it as H. Okay, what should I do now? Remember, we have already calculated fx and fy while we wanted to calculate cx. So these two are known. And this one is also known. Okay? Now, I have four unknowns: hx, hy, dx, and dy. If I take the moment around h, I can find dx and dy. If I take a moment around d, I can find hx. So the question is asking me to find the force at pin h. So there is no point of calculating components of d, right? I just need h, right? So I'm just gonna take the moment around point D. Does it make sense? So I will have f of BE times 24 minus fx times 36 minus fy times 72 plus hx times 36 equal to 0. Because I have all of them, so f of BE, f of x, and f of y, we have already calculated them, 3,000, 1,200, and 2,000. So we can easily calculate hx to be 2,400 pounds. Yeah. Okay. So the line of effect of HY passes through point D, right? So when the line of effect passes through a point, that force doesn't exert any moment around that point. Okay? So now that I have hx, how can I calculate hy? Because usually we write down the moment equation and then we go to the sigma f of y, right? Go ahead.
No, the moment around H to figure out the
Moment around H will give us dx, not dy. Because dy passes through H, right? So even if I have dx, I still don't have dy. And sigma f of y, I have two unknowns, which are hy and dy. So what should I do here? So this is where we get some help from the geometry. Or this sine theorem. So we can say hy over 48 is equal to hx over 24, right? So you have hx and hy. You have an angle here, alpha, and the ratio of hx and hy is the ratio of the front here to the side here, right? So the front is 36 plus 12, 48 over 24. Does it make sense? Yeah? What? Two force member? No. So basically we have a hydraulic cylinder here, okay? And it is bearing a load, okay? And that load is divided into x and y components, and we have the x component and we want to find the y component, okay? You can look at it as, if I had the H force and this angle theta, I could have projected H to HX, right? So now I want to do vice versa. I have HX and I want to project it to H, okay? And the simplest way to do it is using the tangent. So these two, which is here, over this side, which is here, okay? This will give you hy equal to 4,800. So the question was asking for the components of the force exerted by the hydraulic cylinder on pin H. And because it was asking for the components, that's where we leave our answers. If it was asking for the total force, or if it was asking for the tension, stress in the pin, then you should have calculated H as Hx to power of 2 plus Hy to power of 2. Okay? Any questions? No? Do you guys need a break or not? You're good? Okay. The next problem deals with internal forces. I'm just gonna give you guys a moment to read it. Okay, any ideas on how to solve this? Not you. Somebody else. You say something. Yeah. Why not? Just give it a try. You can say draw the free body diagram. That's always valid. After that. Yeah. So the question is saying, knowing that the radius of each pulley is 120 millimeters, and neglecting the friction, determine the internal forces at point C, point J, that is 100 millimeter to the left of point C. So, similar to the first question, go ahead. Say, can you come and sit here so I can hear you? Yeah, exactly. So when we want to find, so that if you want to know the roadmap, when we want to find the internal forces acting at a specific point, we make a cut section at that point. Okay, so right now we know that for part A, we need to cut the beam at point C, and for part B, we need to cut the beam at point J. Okay? So that is the general roadmap. What happened? Did you turn it off or? I was asking, did you turn it off accidentally or? You didn't, that's good. Yeah.
What's that?
It's weird. The computer is still on, but the projector is going to. I don't know. We'll see. Why the doesn't come down? Control.
Let's go down.
Down. Left throw. Maybe. Oh. Okay, there we are. Sorry, guys. Okay, similar to the first question that we had a cable and the tension inside the cable was the same. So here the cable is being pulled with a 600 Newton force, and that force continues to exist all over the place. So here we have 600 Newtons, and here the tension also we have 600 Newtons. So if I draw the free body diagram of our system and replacing the supports with the reactions. At A, we have a roller support, therefore we only have a reaction in the Y direction. And at E, we have a pin support, therefore we have EX and EY reactions. And then we have the cable going through the pulleys. So from the free body diagram, the easiest thing that we can get is solving for sigma f of x and finding that E of x is equal to 0. So that's the first step. What next? Moments at A to find EY, or moments at E to find AY. I want a section at C and J like this, that is shown here. Therefore, I will go for moment around E to find AY, and therefore from there I can make my cuts, okay? But the other way around is also okay. So I will go moment around E equal to 0. And we'll have 600 times 820 minus 600 times 180 minus AY times 1,000 is equal to 0. And we get AY is equal to 384 newtons. Is it clear to everyone? Yeah.
Still don't have the difference, but that's a pin, or is that something else?
Which one? A itself is a pin, but at the bottom you see that it's on a roller. Yeah. So because it's a roller, it can move in the X direction. So it has only a Y component. It, yeah. And we calculated EX to be 0. If E was like this, then it would have had a moment as well, okay? If it was mounted inside a wall or something, without the pin. X, Y, and a moment. Okay, since the only Y components in our free body diagram are AY and EY, we can simply say, using sigma f of y, we can say that EY is also 384. Okay? The only difference is the direction is different. Right? EY is downwards. Okay? Does it make sense? So over 180, 600. So it's 1200, the diameter of pulley, and you gotta subtract it from the distance from the center of pulley to the end point of E, right? I'm sorry, it's not the diameter, it's the radius. So this part is 1200, and if you subtract it from 300, you'll get 180. Okay? Any other questions? Okay. Now there is an angle here from where we have the rope and the pulleys. We need that angle. So sine of alpha is equal to 120 divided by 200. So you have a right triangle here. 120 is the radius of the pulley, and 200 is from here to here. Okay? This is equal to 3/5, and therefore we can say that cosine of alpha is 4/5. And alpha itself is 36.87 degrees. Okay? So I want a section at point C, and I need to replace the pulley with the forces equivalent to the pulley and the rope at that point. So around pulley B, I have a 600 pulling down, and because the cable itself has its 600, so I have a 600 at the angle alpha as well. So if I want to replace that, this 600, the second one, has X and Y components. Which are 600 times cosine of alpha and 600 times sine of alpha. Does it make sense? Do you all understand this? So this pulley, basically, it has a force here as well. And we're modeling that on the rod. Okay? So after that, at point B, I have By and Bx. Bx is equal to 600 times cosine of alpha, and By is the summation of 600 plus 600 sine of alpha. Does it make sense? Yes? No? Maybe? Anyone cares? Yeah. Why not? Can anybody answer this question? He's asking, I've done this, solving for A1 and EX and B1. He's asking why we didn't include those ones while calculating the reaction. Yeah. Because they're internal forces, that's correct. So When you want to calculate the reactions, you don't care about the internal forces, okay? Because they cancel out each other. But when I section my beam, then there is nothing to cancel out that force, and I have a force in the middle, which is the internal force, okay? So looking at the free body diagram of AC, we can write sigma f of x is equal to 0 and find the internal force F at point C. I'm just gonna, because the same notations are gonna be used for both point C and point J. So I will just put a horizontal line here so you guys would know the difference. So f of x will be equal to 600 times cosine of alpha. The internal force F will be 840 newtons. Okay, let me write it like this: 600 times 4 over 5, 480 newtons. And writing sigma f of y we have V plus 600 plus 384 that we calculated before minus 960 equal to 0. Therefore, V is equal to 576. Does anybody know where did the 960 came from? So I have the free body diagram on the left, and I have a 960 here. You don't know? He knows. Ask him. You should know, right? Because you're playing Clash of Clans. I figure. Yeah, it's the by component, the summation of 600 plus 600 times sine of alpha. So it's this component, by. Okay. And finally, taking the moment around C gives us M minus 0.5 times 384 plus 0.2 times 960 equal to 0. And quite frankly, if you calculate it, M is equal to 0. You could have foreseen this because we have symmetry in the whole truss, and C is located exactly in the middle. Therefore, the moments caused by these two forces around it are zero, and all the reactions. Okay? But what about point J, which is here? 100 millimeters to the left of point C. So writing sigma f of x equal to 0 for point J will result to the exact same thing as above. F equal to 480. Sigma f of y will result to V equal to 576, right? Because we don't have any external forces acting between these 2 points. So their axial and lateral internal forces are exactly equal to each other. Okay? Between point B and point C. Okay? And the same as if I had taken this point D. But if I go here, because we have an external force here, then the vertical will be different. Anyways. If I take the moment around J and equate it to 0, I will have M minus 0.4 times 384 plus 0.1 times 960 equal to 0. Therefore, the moment at J will become 57.6 Newton meters. Any questions? Okay. Next question? Okay. Does anyone have any questions? No? Okay. I will share everything with you guys, so don't worry about writing them down. Mostly try to focus on figuring out what is going on and come up with a question if you have. Okay? Okay. I see that it's 15 minutes to 8, so I would say we skip this one and go into the mechanics of material problem. Okay, so this question is a good one. It's killing a couple of birds with one stone. So we have thermal stress, thermal expansion. We have aesthetically indeterminate structure. So this would be a good example to come from the first chapter, from the third chapter of Mechanics of Material in the final exam. I will give you guys a moment to read it. Okay, any ideas on how to solve it?
Stressful, right? That's what. Did you use any other formulas besides from this question?
Aside from the stress formula? Yes, the deformation formulas. Yeah, I will write. Okay. So we know that part 1 has an initial length of L plus delta, and it was cooled down, so it had a negative deformation, and then it was placed between points A and B, and then when it warmed up, it is now posing a force to the other element, element 2. And the nature is a thermal stress, thermal deformation, and because both sides are clamped, we have a statically indeterminate structure. So I'm gonna start by writing the known things. We know L1 is equal to L plus delta. We know L1 star is equal to L2 equal to L. The cross section of the first element, we call it A, and the cross section of the second element is given to be 1.8 times of A, or for simplicity, I can write as 9/5 times A. Okay? And their modulus of elasticity, E1 is equal to E2 equal to E, because they're both the same material. First, we're gonna start by finding the stresses sigma 1 and sigma 2. So I will draw the free body diagram. Element 1 and element 2. I have F1 here and F2 here. And this in the middle is point B. writing sigma f of x equal to 0, we figure out that f1 is equal to f2. Now, the elongation or deformation in element 1 is equal to f1 times f1, which is its length, L1 star, divided by A1 E1 times F1. And the reason I'm putting the subscription for them is that in the exam you might have different cross sections and different materials, so then they would be different. Here they will be simplified further, so I know that it's L over A E times F1. The F1 is unknown, and similarly I write this for E2, F2 times F2, L2, A2, E2 times F2. And substituting the cross section 9 over 5 in the denominator, it will come out and become 5 over 9 times L over AE times F2. Okay? Now, what else can I write here? I know that initially this rod was this size and it was deformed to the amount of delta to be fit in the gap, right? So I know that the total deformation happening in element 1 and element 2 is equal to delta. Does that make sense? I feel like it doesn't make sense to any of you guys. You just finished this chapter? Okay. So what we're doing here is called superposition. So we assume that they can expand freely, and then we put the limit on that expansion, which we know from the geometry. Okay, does it make sense? I hope it does. So we know that E1 plus E2 is equal to negative delta, right? So delta is the excess of length that we had in element 1. Okay? So did you read the question? Yeah. So the question is a bit tricky because you have lots of variables that you need to use in order to solve the equations, but you don't know their values. And they basically, you just use them to solve the question. And that delta is one of them. So element 1 was originally, so we have a length of 2L here, okay? One of the components had a length of L, and the other one needed to have the length of L as well to be fit in the gap, okay? But it had a length of L plus delta. So they froze it to be contracted and be fit into the gap. After that, when they're left in the room temperature, because of the thermal stress, it wants to expand, right? But now the other element is there, not letting it to expand, basically. If it wasn't there, it would just expand to the initial size of, I'll get to you, to the initial size of L plus delta, right? But the other element is there and it's preventing it. So we have written down the equations. They will both deform to some extent, and that extent is E1 plus or E2 based on their cross section and the modulus of elasticity as given here. And we don't know E1 or E2, but we know that the total deformation from E1 plus E2 is equal to the initial deformation that we imposed to the member 1, right? And that is E1 plus E2 are equal to negative delta. Yeah, you had a question. Did I answer it or you forgot it? Go ahead. Why is delta negative? Because we have compressed the element and we have got to delta. Okay, that's why. If it was, for example, if it was another question and you had two elements like this, and then you had a wall here, this is also one of the common ways of giving this. And then they would tell you that we have a delta T of, I don't know, 100 degrees. So here you'll have a delta, and because of this delta T, you will have, let's say this is 1 and this is 2, you will have E1 and E2, okay? And the sum of E1 plus E2 will become delta, okay? Because they're expanding. Yeah, because there is a space, right? Here, in our question, it's vice versa, okay? So they're being compressed, okay? And the total amount of compression is equal to negative delta, okay? Displacement, yeah. Deformation. Yes. Okay. You have a question? No? Okay. Let's get back to this. Now, putting these two equations, equation 1 and 2, into equation 3, and also taking the account that F1 and F2 are actually equal to each other, we'll end up having L over AE times F1 plus 5 over 9 L over AE times F2 is equal to negative delta. taking into account that F1 is equal to F2, we can write that F1 is equal to F2 equal to negative 9 times A E delta over 14L. Okay? This is simply calculated by taking the common denominator and adding up those fractions. Okay? Now, what are we solving for? The question is asking us to determine the expression for a stress sigma 1 induced in element 1 and the stress sigma 2 induced in element 2. So now that I have the forces acting on element 1 and 2, I can write the expression for the stress. So sigma 1 sigma 1 is equal to F1 over A1 equal to negative 9E delta divided by 14L. And similarly, sigma 2 is equal to F2 over A2 equal to negative 5 times E delta over 14L. Okay? So if they had given us the values, we could have solved for the stresses, right? So don't freak out. It's just, it can be replaced by numbers, right? Any questions up until here? Yeah. A small f? No, it will be given to you. Okay, now moving to the part B, which it says determine the amount of UB by which element 2 is shortened when element 1 is forced into the dashed line. Okay. Now the displacement at point B UB is equal to negative E2, the deformation of the second element, right? It is equal to negative F2 times F2 equal to negative 9 over 5 L over AE times negative 9 times AE delta over 14L. And crossing out the variables, we will end up with having 5 over 14 times delta. So does anybody know the difference between U and E? Yeah. Okay, any questions? Yeah. 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 Because they have different cross sections, different areas. So the area is given here. A2, yeah, A2 has an area of 1.8 times A. So they are saying to assume the area of the first element is A, and the area of the second element is 1.8 times A. What? A is not. I can't hear you. 14L? No. No. Okay. Let's move to the next question. This one. So if you guys have just finished this chapter, do you guys even know the torsion? No? You haven't been taught? Oh, okay. 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 I'll try. So basically, the same concept applies, just before for actual compression, we use F is equal to L over AE. For torsional deformation, we use a different F. F is equal to L over GI. Okay? So basically, the modulus of elasticity is replaced by the shear modulus, which is G, and the area is replaced by I, which is the second moment of inertia of the cross section. Okay? So the concept remains the same. Okay, I'll give you guys a minute to read the question and try to come up with possible scenarios, at least the ones that have had the lecture.
So finish at 9. Finishes at 9. I'm gonna say a few words here about where the resources are in the anonymous feedback form, and I'm gonna let you take the show and be like, hey, say I'm your first year rep. Help you on the academic team. Thank you for coming. You're gonna do all the closing stuff. And like, we got tickets for you. Come line up and the rest of the study will go for you. So you don't be shy. Everyone takes one, and you can take one once everyone has one. So before I end that, you offer it to the TA. These guys just heard that again.
So if I take counterclockwise as positive, I'll end up having TA, let's just call this TB, TA minus TB equal to 0. Therefore, TB is equal to TA equal to 400 Newton meters. Okay? Assuming, for example, we could have had something here, like another pulley or something, and or simply something like this. If we had something like that in the middle, then it would have become, hypothetically, I'm just gonna write it here because this equation was too simple. I just want to give you guys another scenario. If we had a T1 in the middle, then our equation would have become TA minus T1 minus TB equal to 0, and TB would have become TA minus T1, right? So we don't have that. It's very simple and straightforward in this question. And we find TB to be equal to TA. Okay? What is next? Now we need to relate TC to TB by analyzing the gears that mesh them together. So I don't know if you guys have passed mechanics of machines or not. Have you guys passed that? No? So between the two gears, when we have two gears in contact with each other, the force in the middle is equal. Okay? So the forces are equal to each other because the gears are meshed together using two teeth, basically, and based on the third law of Newton, the action and reaction are equal to each other. So the force between the two meshed gears are equal to each other, right? I can write the moment as F times the radius, right? So if I have two meshed gears, let's say this one is B and this one is C, I can write that TB is equal to F times RB and TC is equal to F times RC. Right? Therefore, I can relate these two together because the two F's are equal. From here, I can write TC is equal to RC over RB times TB. And I know from the geometry that when this one is going to the right, the upper one will go to the left. Okay? So direction-wise, they're in the opposite direction of each other. So I'll just add a negative there. Okay? Substituting the values for the diameter of gear B and the radius of gear B and the radius of gear C, which are given here, 150 and 75, we can find TC to be negative 200 Newton meters. Okay? Now we need to calculate the polar moment of inertia of the shaft for each shaft. The polar moment of inertia, which is used in torsion, is P d to power of 4 times 32. This is for a circular section. Okay? You will be given the formula for that. Okay? So we need to calculate the polar moment of inertia for each shaft. Substituting the values, we have what are the values? What are the diameters? It's 32 millimeters, right? So substituting P times 0.032 to power of 4 divided by 32 gives us 1.0294 times 10 to power of minus 7 meter to power of 4. Okay. Now, the shear stress is the torque times the maximum distance from the center of the shaft times the polar moment of inertia. So the maximum distance from the center of the shaft is the radius of the gear, right? Is the radius of the shaft. Sorry. So it will be so for shaft 1, T1 will be T1 D over 2 times IP. Substituting the values, we have T1 so T1 is equal to TA, so 400 times 0.016 divided by 1.294 10 to power of minus 7. Okay? So the stress becomes 62.17 megapascals. So converting 10 to power of 6 to megapascals, we'll end up having this value as the torsional stress in the shaft. Okay? Following the similar equation, in the second shaft, we have T2 D over 2 over IP, and T2 in the second shaft is equal to TC, which we calculated to be 200. So it will be 200 times 0.016. The diameters are the same, divided by 1.0294 times 10 to power of negative 7. And this one will become 31 point, where is it? 085 megapascals. Okay? So part A was asking us to determine the maximum shear stress in each shaft. So we did that. Now moving to part B is asking us to determine the angle of rotation of the gear A relative to its no load position. Okay. Do you have any questions up until this part? How many of you have actually had this lecture? Only one? Okay. So not having any questions makes sense. Okay, just because you didn't have the lecture doesn't make this problem too complicated. Okay? So think of it as before we used to have non-rotary structures, and then you would write the equilibrium in X and Y and Z directions, right? Now we have a rotary structure and we write the equilibrium just by writing the moment equilibrium, okay? So obviously we're not exerting any force in the X or in the, so if I put the two other axes like this, let's say this is Z, this is Y, we're not inserting any forces in the Z and Y direction. We're just inserting a moment around the X axis, okay? And then we write the moment equation. In the exam, you might have several torques in the middle of the shaft, so you just add them up together based on the direction, positive, negative. You assume one direction positive and the rest of the opposite direction will be negative. You add them up together until you find the torque at the end of the shaft, and then it is transmitted to the other shaft using a gear. When we have a gear, the force between the two gears are equal, and the force times the radius gives you the torque. So we have the torque at one end, and we can convert it to the torque to the other end, to the other gear, basically. When we have the torque to the other gear, we can find the torsional stress in the shafts. So that's what is important for us, the torsional stress in the shafts. The formula is T times C over polar moment of inertia, and C is the maximum distance from the neutral axis of the shaft, which is the center of it. Okay? So the rest of them is just substituting the values into formula. That's basically the overall concept of it. Okay? Does that make sense? Okay. Okay, moving forward for part B, we want to calculate the torque twist flexibility of the elements of the shafts. So the formula for that for the first element will be, so the general formula is L over GI. So for the first shaft is L1 over G times IP. Both shafts have the same shear modulus. Both of them have a shear modulus of 80 gigapascals, and they just have different lengths. So for the first shaft, it will be 1.2 meters times 80 times 10 to the power of 9 times 1 point, the polar moment of inertia was 1.0294, 10 to the power of -7, which will give us 1.4571 times 10 to the power of -4. And the unit for this is radians per Newton meters. And for the second shaft, it will be L2 over GI. So it will be the same thing in the denominator, The only difference is now we have 0.5 in the denominator, and it will result to 6.0713 times 10 to power of -5 radians per Newton meter. Okay? Okay. Okay, now we want to calculate the deformation. So we have a torsion in this shaft. Shaft 1 can rotate, okay? Shaft 2 is restrained in the wall. So shaft 2 basically wants to stop shaft 1 from rotating, okay? Does it make sense? Okay. So basically the geometry here, it dictates us that the total deformation from point in shaft 1. So have you guys ever tried to dry a wet shirt or something? You rotate two ends, okay? So if you want to calculate the total deformation in that shirt, what you do is that you subtract the deformation at two ends from each other, right? Because it's relative to each other, you subtract it and you get the total deformation in your shirt, for example. Does it make sense? So if I want to twist something and I'm twisting the two sides differently, the twist of the whole thing is the twist of this side minus the twist of the other side. Does it make sense? Okay, so the rotational deformation of shaft 1 is the deformation at point A minus the deformation at point B. So point A is one side of shaft 1 and point B is the other side. Okay? And for shaft 2, because so the same thing goes on for shaft 2. So phi 2 would be phi of C minus phi of D. But because D is a wall, this term is 0. So for shaft 2, phi 2 is just equal to phi of C. Okay? Now we need to figure out the relation between phi at point B and phi at point C. Remember, I told you that the force between the two gears is the same. So we came up with an equation between their torques and their radius. So similarly, we can come up with an equation for their deformation. I'm just gonna draw them again. This is gear C, and this is gear B. So the formation at B times the radius of B is equal to the formation at C times radius of C. Why? Because the displacement in the middle is the same. The two gears are meshed together, therefore they're gonna deform the same. What? Where's R? R is the radius of each gear. So this is RB, and this is RC. Okay? So rotational deformation times the radius gives you the linear displacement or the linear deformation. And because the two gears are meshed together, the linear deformation between them is equal to each other. Right? So we write this equation, and from this we get phi of B is equal to negative RC over RB times phi of C, because they're in the opposite direction of each other. Okay? And we know that phi of C is equal to phi 2, so this will become negative RC over RB times phi 2. Okay? Any questions until here? So the deformation phi is given by F times T. So for each shaft, we have previously calculated the F. Okay? Just note FT. FT is called the torque twist flexibility. So in previous chapter, if you remember the previous question, we solved for these small f's. These are the axial flexibility of a rod, right? Now we solve for torsional flexibility, and multiplying it by the torque, we get the deformation, right? So I can write phi of A is phi 1 minus phi B and I can substitute phi B as the equation I got here. So it will become phi 1 minus RC over RB times phi 2. Okay? Now, substituting phi 1 and phi 2 with their torque twist flexibility, I can calculate phi of point A to be f of T1 times T1 minus RC over RB f of T2 times the torque in the second shaft, which will become 1.4571 times 10 to the power of negative 4 times 400, which was the torque at point A, minus 150 over 75, which is the ratio of the radii, times the torque twist flexibility of shaft B, of shaft 2, 6.0713 times 10 to the power of minus 5 times negative 200. Okay? Calculating this value gives us phi at point A to be 0.0644 radians. Do you have any questions? The ones who survived will pass the course. Any questions? No? Yeah, that's it. Now we get to the questions and answers. What? Do you have any questions regarding previous chapters, this chapter, life in general?
How many of you guys are in electronics? Are you guys all taking